learned about refraction of light, and you all know that refraction means bending of light as it goes from one transparent medium to another. Now, we also discussed that extent of bending is not the same. Extent of bending for different pair of media is different. That means when a ray of light goes from air to glass, it may not bend to the same extent as it goes from air to water. So how can we find out that, to what extent it bends? That we are going to learn today. So we are going to talk about the laws of refraction and refractive index, a very important term. Okay. So as you can see, I have already written the laws of refraction. There are two laws of refraction. You have already done two laws of reflection. Similarly, there are two laws of refraction. The first law says that the incident ray, refracted ray and the normal to the interface of the two transparent media at the point of incidence all lie in the same plane. What does this mean? This is the diagram. Let's say this is the line dividing the two media. This is medium 1, which let us say it is air, and this is medium 2, let us say it is glass. This is the ray which is traveling in medium 1, so we call it incident ray. As it goes from medium 1, which we have taken air, to the medium 2, which is glass, it will obviously bend, and it is going from air to glass, and we already know when it goes from rarer to denser medium, it bends towards the normal. So if we've shown it bending towards the normal, and this ray which is traveling through the second medium, glass, is called refractive ray. So the first law says that incident ray, refracted ray and the normal at the point of the incidence, this is the point of incidence, all lie in the same plane. These three rays lie in the same plane. This is first law. That means they are, as I have drawn in this 2D plane, they all lie in the same plane. It's not that if this is incident ray, this is normal, refracted ray will not go into the third dimension, it will lie in the same plane. This is law 1. Now second law is a very important law, which is also called Snell's law. Snell's law says that for a given pair of media and a given color of light, the ratio of sine of I to sine of R is a constant, which is equal to n to 1, and n to 1 actually represents refractive index of medium 2 with respect to medium 1. Fine. For example, here I have taken a pair of media. Now this law says that ratio of sine I to sine of R is a constant for a given pair of media and a given color of light. That means if it will be constant for a given pair. Here I have taken air glass medium. If it is air to water, the value will be different. If it is glass to water, the value will be different. For a given pair of media, it is constant. So here it will be, so if we go by this, sine of I, angle I, by sine of angle R will be equal to n to 1. Now n to 1 is refractive index of 2, medium 2 with respect to 1. If I apply it here, I can say in this case sine of I by sine of R will be equal to refractive index of second medium. Second medium is also always the medium through which the refracted ray travels, and first medium is the medium through which the incident ray travels. So refractive index of second medium, that is glass, with respect to first medium, which is air here. So sine I by sine R in this case will be equal to NGA, refractive index of glass with respect to air. And this ratio is constant for a given pair of media. That means this ratio for if I take another pair of media, this ratio will be, the value will not be same as for air glass medium. Okay? So, and it is also constant for a given color of light. This will take up. While talking about dispersion, this will be more clear why we said so. Okay. Okay, so this is law 1 and this is law 2, which is also called Snell's law. From here, from the Snell's law, we can say, if I am given a particular value of I, let's say angle I is 30 degree. Fine. Then sine of 30 degree by sine of R will be equal to this value, refractive index of glass with respect to air. And if I know this value, I can find the value of R. Fine. What will be the value of R, angle of refraction, I can find out for a particular value of I if I know this value NGA, refractive index of glass with respect to air. So actually this value decides the value of R. The value of R depends on this value, NGA, refractive index. So refractive index tells us to what extent bending of light takes place. Fine. Now R is less than 30 here, as we can see, but less than 30 can be 20, 22, 18, 19, any value in fact it can be. But what value it will be depends on the refractive index of glass with respect to air. If I know this value, I can calculate the value of R for a particular value of I. Right? So refractive index actually tells us to what extent a ray of light bends as it goes from one medium to another. Now we are going to talk about refractive index in details. Fine. So I am rubbing this. Now refractive index, that means, is the extent to which the bending of light takes place as it goes from one medium to another, can be found by the term refractive index. Fine. How can we calculate? How can we find refractive index? Now we are going to define refractive index in terms of the relative speed of light in the two media through which the light is traveling. Fine. Let's say, again I am drawing, let's say this is medium 1, this is medium 2, and a ray of light goes, and as it goes it bends. This is how. So this is incident ray, refracted ray. Okay. Let me take again this as air, for example, and this as glass. Let's say the speed of light in medium 1, let's say, is V1, and speed of light in medium 2, let's say, is V2. Now I can define refractive index of medium 2 with respect to medium 1. I can calculate how. I denote this term as N21. It can be calculated by the formula speed of light in medium 1 by speed of light in medium 2. That means I can say N21 is speed of light in medium 1, which I have said is V1, by speed of light in medium 2, which I have said is V2. This is how I can calculate the refractive index of medium 2 with respect to medium 1. This is one of very important formulas of refractive index. For example, now, let me take one example here. Speed of light in air we know is 3 into 10 raised to power 8 meter per second. And speed of light in glass I am giving to you is 2 into 10 raised to power 8 meter per second. If I have to calculate refractive index of glass with respect to air, fine, it will be refractive index of glass with respect to air means speed of light in air divided by speed of light in glass. So this you have to remember, N21 is V1 by V2. First medium in the numerator, speed of light in the second medium in the denominator. So it will be speed of light in air by speed of light in glass, which we know is 3 into 10 to the power 8 by 2 into 10 to the power 8. And that will be 3 by 2, and that is almost 1.5. And you know refractive index will not have any unit because it is the speed of light and the unit gets cancelled. It's the ratio of speed of light. So it will not have any unit. We will say refractive index of glass with respect to air is almost 1.5 here. Fine. So this example I have taken to explain how we decide how do we calculate, and we know that in the numerator we have speed of light in medium 1 and denominator speed of light in medium 2. Fine. So this is how we do it. Let's move on to further. So as I've said, let me drop this. I've said N21 is V1 by V2. Similarly, I can say N12 I can say will be equal to refractive index of first medium with respect to second medium will be just opposite of this, which will be V2 by V1. Obviously, with the same logic. Fine. So this is one of the formulas of refractive index of medium 1 with respect to medium 2. Now in your book it's a table of values of refractive index is given. Fine. But we've just seen refractive index of glass with respect to air will have one value. If we calculate refractive index of glass with respect to water, let's say, it will have another value. Refractive index of glass with respect to Kerosene will have another value. So value will depend on as the pair of media keeps changing. So what value can be given in the table? Now that value is of the absolute refractive index of the medium. Now how do we define absolute refractive index of a medium? Absolute refractive index of a medium is the refractive index of a medium with respect to vacuum or air. Fine. So we denote it with Nm. So absolute refractive index is the, let me write, refractive index of a medium with respect to vacuum, or we can also say air, because air, the speed of light in air is almost the same as the speed of light in vacuum, and we denote it with Nm. Fine. So it is with respect to speed of refractive index of the medium with respect to air. That means medium 1 is air and medium 2 is the medium. So we will have in the numerator speed of light in medium 1. So it will be speed of light in vacuum or air divided by speed of light in the medium. So that will be what? So Nm will be equal to C, which we know we used to denote speed of light in vacuum or air is denoted by C divided by speed of light in the medium, which is V. Fine. So this is the formula for absolute refractive index. Okay. So we have done that N21 is V1 by V2. Second formula, absolute refractive index Nm is C by V. Fine. Because here the first medium is vacuum. So we have in the numerator we have written C, and second medium is the medium itself. So the speed of light in the medium is V. So this is how we write. Fine. So this is about absolute refractive index. Now, so we have done two formulas. Let me write the formulas I have just done for you. And we've done N21 is V1 by V2. And we've done Nm is C by V. This is refractive index of medium 2 with respect to medium 1. This is absolute refractive index of a medium. So the values that you get in the table in your book are the absolute refractive index of the various media. That means the refractive index of the media with respect to the vacuum or air. Now, there's one more formula that we derive. Now, let's say there are these are two media. Let me say N1 is the absolute refractive index of medium 1 and N2 is the absolute refractive index of medium 2. Fine. So in terms of these, if I have to write N21, N21 is equal to N2 by N1. This is the third formula, which we can even derive using these two formulas. This is first formula that we discussed. This is second formula that we discussed. This is the third formula I am telling you about refractive index. This can be derived. N21 is N2 by N1. How we can derive it? Let me tell you that. Okay. Now I know N2 can be written as C by V2 and N1 can be written as C by V1. This we know. If N2 is the absolute refractive index of medium 2, so it is C by V2. N1 is the absolute refractive index of medium 1, so it is C by V1. Where V1 is the speed of light in medium 1, V2 is the speed of light in medium 2. I can also write that N21 I know is V1 by V2. Fine. So I have this formula and these two, and I'll use them to derive this formula. From here I can say V1 is C by N1, and from here I can say V2 is C by N2. So N21 is V1 by V2, C by N1 upon C by N2. N21, C by N1. When it goes in the numerator, we take the reciprocal, so it will be N2 by C, and you can see C gets cancelled and we get N2 by N1. This is how we've proved that N21 is equal to N2 by N1. I hope you have understood. Fine. So we have three formulas that we've done for refractive index. N21 is V1 by V2. Nm, the absolute refractive index, is C by V. And N21 can also be written as N2 by N1. Fine. I'm rubbing this proof which we've used to prove that N21 is N2 by N1, and I'm going to tell you the difference. How can we use these formulas actually? Let me tell you. I'm writing it here. N21 is N2 by N1. For example, if you're given speed of light, let's say you're given speed of light, I'm taking the same example as I took in air, and speed of light in glass. This is 3 into 10 to the power 8 meter per second. This I've already done, but let me take it once more here to tell you the difference. Now, if I have to calculate refractive index of glass with respect to air, I have to write the speed of air in numerator. So it will be VA by VG, which will be 3 into 10 to the power 8 upon 2 into 10 to the power 8, which is same, and we know it is 1.5. But if I am given here, suppose I am given absolute refractive index of glass is given to me as 3 by 2, and absolute refractive index of water 4 by 3. Okay. So what I'm given is, I'm given Ng as 3 by 2 and Nw, which is for water, is 4 by 3. This is given to me. I have to find out the refractive index of glass with respect to water. So what will I do is, I'll write this in terms, this is refractive index given to me, so it will be Ng by Nw, refractive index of glass in the numerator and water in the denominator. That will be 3 by 2 divided by 4 by 3, and you can then find the answer. It will come out to be 3 by 2 into, we'll take the reciprocal, 3 by 4, that is 9 by 8. Okay, so when we are given speed of light, N21 is V1 by V2, numerator, first medium in numerator, second medium in denominator. When we are given the refractive index of the medium, then if you have to calculate N21, N2 numerator, N1 denominator. Refractive index of second medium in the numerator, refractive index of first medium in the denominator. So these are the two examples that will help you to understand the difference between this and this, how to use these formulas to solve questions. Okay, fine. So let's talk further about refractive index. Now, what does the absolute refractive index of a medium indicates? Fine. So there is a table given in your book, and I'm writing the refractive index. Now, first of all, let me tell you, this is absolute refractive index, it's C by V. From here we know, greater the refractive index of the medium, lesser is the speed of the light in the medium. Higher Nm, less is the V. Okay, that means higher the value of the absolute refractive index of the medium, lesser is the speed of light in the medium. That means it is optically denser. More is the optical density. Fine. Jitna zyada, that means absolute refractive index. Higher the value of absolute refractive index, higher is the optical density of the medium. More the optical density. So, if I have given 2-3 media and you are asked to compare their optical density by looking at the value of refractive index, more the value of the refractive index, more is the optical density of the medium. For example, I am giving you absolute refractive index of water is 1.33. Absolute refractive index of kerosene is 1.44. Absolute refractive index of turpentine oil, these are given in your book, turpentine oil is 1.47. So if we compare these three values, which one is the highest optical density? Turpentine oil obviously has the highest optical density. It has the highest value of refractive index. So more is the optical density. Then comes kerosene, and then comes water. That means this has optically denser than kerosene. Kerosene is optically denser than water. That means if we compare the speed of light will be highest where? In water, because water has least optical density, so speed of light will be highest in water. Now here also comes the concept of optical density and mass density. We discussed in the previous class also. Optical density is different from mass density. We all know that water is denser than kerosene or turpentine oil. You all know that kerosene floats on water. So kerosene is less dense. Mass density of kerosene is less than water. Similarly, mass density of turpentine oil is less than water. But here we see that from the value of the refractive index of these three media, we see that turpentine oil and kerosene have greater optical density than water, although their mass density is less than water. That means optical density and mass density are different. Optical density depends on the speed of light in the media and the refractive index. Higher the refractive index, higher the optical density, and least is the speed of light in the media, right? So we can use these values of refractive index. There can be many questions asked. So if you are asked, how will a ray of light bend as it goes from water to kerosene? Fine. As it goes from water to kerosene, water is optically less dense than kerosene from the values we can say. So this is denser. So ray of light going from water to kerosene will bend towards the normal. Fine. So such questions can be asked based on the values of refractive index. So today we've discussed refractive index, and the conclusion is refractive index tells us the extent to which the bending of light takes place, and the higher the refractive index of a medium, higher is the optical density of the medium, and the formulas we've already discussed. We may discuss, if you want, more numericals on refractive index. You can write in the comment box if you want, and we can do a few more numericals on this in the next class maybe. And thank you. That's all for the day. Thank you.